Previously, we covered the core foundations. Now, in part 2, we tackle Phobos, fate and exploration value. Phobos is falling, not quickly, not dramatically, but measurably, steadily, and with a clock attached. And that makes it one of the most interesting objects in the inner solar system right now, for reasons that go well beyond the spectacle. In the first episode of this series, we looked at what Phobos actually is, its size, its surface, its strange, grooved terrain. This episode picks up that thread and pulls it forward. The question we're answering today is this: what is Phobos' long-term fate, and what does that mean for exploration before it's gone? Because before it's gone is not a figure of speech. There is a real timeline here, and it matters for how we think about Mars exploration in the coming decades. Let's start with the orbit. Phobos sits closer to Mars than any other moon sits to its parent planet in the solar system. At its center, it orbits just 9,376 kilometers from Mars. That is not from the surface. That is from the center of the planet. From the Martian surface, it's closer to 6,000 kilometers up. For comparison, our own moon sits around 384,000 kilometers from Earth's center. The gap between those numbers tells you everything about how unusual Phobos' situation is. It completes a full orbit in just 7 hours and 39 minutes. Mars itself takes 24 hours and 37 minutes to rotate. So Phobos actually overtakes Mars's rotation. It rises in the west and sets in the east, the opposite of every other moon in the solar system, as seen from its host planet's surface. If you were standing on Mars, you'd see Phobos cross the sky in about 4 hours, moving noticeably as you watched it. That speed matters because of what it's doing to the orbit over time. When a moon orbits faster than its planet rotates, tidal forces work against it. The gravitational interaction between the two bodies doesn't pull the moon outward, the way Earth's tides are slowly pushing our moon away. Instead, the tidal bulge on Mars is dragged slightly behind Phobos, and that creates a gravitational pull that slows the moon down and draws it inward. This is measurable. Phobos is approaching Mars at a rate of approximately 1.8 centimeters per year. That sounds trivial, but it compounds, and it leads somewhere definite. Now, here's the part that I want to hold for a moment, because it splits into two very different outcomes, and which one happens depends on a property of Phobos that we still don't fully understand. Models suggest Phobos will reach a critical threshold, called the Roche limit, in somewhere between 30 and 50 million years. The Roche limit is the distance at which Mars's tidal forces will overcome the internal strength holding Phobos together. Inside that boundary, a body can no longer hold itself intact through self-gravity. What happens then depends on what Phobos is actually made of. If Phobos is relatively solid, a coherent rocky body, it may survive the Roche limit long enough to impact Mars directly. That would be a significant collision event, a body roughly 26 kilometers in its longest dimension hitting a planetary surface. But if Phobos is loosely held together, a rubble pile, or a body with a substantial interior void, it may break apart before it ever reaches the surface. In that case, it would form a ring around Mars, a thin, diffuse ring of debris spread out along its orbital path. Mars would briefly join the ranks of ringed planets, though nothing like Saturn. More like a dusty halo that would itself gradually decay over millions of years. We genuinely do not know which of those outcomes is more likely, and the reason we don't know is the reason Phobos keeps coming up in mission planning conversations. Here's what we do know about its composition and where the uncertainty sits. Spectroscopic observations suggest Phobos has a surface that resembles carbonaceous chondrite material, the same family of primitive carbon-rich materials found in certain asteroids. That's interesting on its own, because it links Phobos to some of the oldest and most chemically unaltered material in the solar system. But here's the problem. The reflectance spectrum of Phobos doesn't match any meteorite class we have in our collections particularly cleanly. The surface is extremely dark, an albedo of around 0.07, meaning it reflects only about 7% of sunlight, and it's been heavily processed by space weathering, micrometeorite impacts, and radiation exposure over billions of years. Its density is the other puzzle. Phobos has a bulk density of roughly 1,876 kilograms per cubic meter. That is low. Carbonaceous chondrite rock typically runs higher than that. The numbers suggest Phobos may be somewhere between 25 and 35% empty space, porous, fractured, possibly rubble in structure. That porosity is what makes the ring scenario genuinely credible. This connects to the oldest open question in Phobos research, and I'll come back to close it in a moment. Where did it come from? There are three serious hypotheses. First, Phobos formed in place around Mars from material in the early Martian disk, the same way planetary moons typically form. Second, it was captured. An asteroid or trans-Martian object that was gravitationally caught by Mars early in solar system history. Third, and gaining traction in recent years, it formed from debris ejected by a large impact on Mars itself. Each hypothesis has problems. In situ formation struggles to explain the composition. Capture is dynamically difficult, slowing an object enough to enter a stable orbit without a thick atmosphere or another mechanism is not straightforward. The giant impact hypothesis is cleaner in some ways, but requires a specific sequence of events early in Mars's history. The Japanese Space Agency, JAXA, is currently running a mission specifically designed to help resolve this. Martian Moons Exploration, MMX, launched in 2024 and is en route to the Martian system. Its primary goal is to land on Phobos, collect a surface sample of at least 10 grams, and return it to Earth. If that sample makes it back, we will have actual Phobos material in a laboratory. The compositional match, or mismatch, with asteroid families and Martian surface rocks should tell us something definitive about origin. That's the loop I wanted to close. The origin question isn't just academic. Knowing where Phobos came from tells us what kind of material it holds, which feeds directly into the structural question, which feeds directly into whether it becomes a crater or a ring. And it has one more layer of relevance that I think is easy to miss. Because of its low gravity, surface gravity, of about 0.0058 meters per second squared, roughly 0.5% of Earth's, and its relatively stable, low-energy orbit, Phobos has been seriously discussed as a staging point for crewed Mars exploration. You could park infrastructure there with relatively little fuel cost compared to landing on the Martian surface and fighting its gravity well each time. Remote operations, fuel depots, communication relay. The location has genuine practical value. Several mission architecture studies have included Phobos as an intermediate stop. That discussion has a time limit, loosely speaking. Not a human timescale one. 30 to 50 million years is not an urgent deadline. But it frames the conversation usefully. This moon has a natural end state. What we learn from it, and potentially what use we make of its orbit, is on a planetary clock, even if not a human one. Next episode, Part 3, takes on the next key question in this series, and it's one that touches on everything we've built up here. If you want to follow the full picture as we build it, the Phobos playlist has every episode in order. If you found this useful, and you're not already subscribed, it would be good to have you along. New episodes go up regularly, and the next one continues directly from here. That is part 2 of Phobos. Subscribe so you do not miss it.